Okay, using a cathode ray oscilloscope is something that you have done before in National 5, so you should be familiar with it. All it takes is a little bit of reading from scales. So measuring potential difference is the stuff that you did in National 5. So the bigger the potential difference applied across the Y plates of a cathode ray oscilloscope, the greater the deflection of the spot. Okay, so basically if it's 1 volt, it might go up 1 division. If it's 10 volts, it might go up 10 divisions, depending on the scale that you've got set. So the Y gain control indicates the potential difference required to deflect the spot by 1 division. So it sets the scale. So for example, a setting of 2 volts per division means that every division gives you 2 volts. So a potential difference of 2 volts applied to the Y inputs will deflect the spot by 1 division. So when it says spot, it means like division, like it could be a square. So each square is 2 volts. So if it's 2 squares up, it'd be 4 volts. So assuming a setting on the Y gain control of 5 volts per division, indicate in the diagram opposite the position of the spot when A, 15 volts DC is applied to the Y input. Okay, so 15 volts. So we said it's 5 volts per division. So 1 would be 5, 2 would be 10, 3 would be 15. So get rid of those first 2 spots. That there is 15 volts. Okay, so basically it would be 3 squares up from the middle line. Part B, 10 volts DC is applied to the Y input with the opposite polarity to A. So that means going down instead of up. So if you'd gone down first of all, you go up this time round. So, but we've gone up first of all, 3 squares. So this time it's 10 volts. So 5, 10 there. Get rid of that first spot just so we don't confuse anyone. So it's 2 squares down in the opposite direction. Okay, the next one. Assuming a setting on the Y gain control of 0.5 volts per division, so each square is 0.5 volts, what is the potential difference represented by A and B? Okay, so 0.5 volts per division. I'm going to zoom in a little bit more now. So going up from the center line, so that's 0.5, that's 1, that's 1.5, that's 2. So that's 2 volts. And for part B, 0.5 volts per division, so 0.5, 1, 1.5 volts, so 1.5 volts. And you could basically say it's the opposite polarity if you wanted to. It's not asking you, but it's quite good to put in our notes. If an alternating potential difference is applied to the Y inputs, the trace shown is obtained. The trace does not give us any information of the frequency of the alternating potential difference. Okay, so again, it tells us the voltage because you can just work out. So if that was 0.5 volts, all you would do is go, right, okay, 0.5, 1, 1.5, 2 volts, and it's the same down because it's AC. So 2 volts. So that's what we've done before in National 5. In higher, we have a little bit of added extra going on here. So we're measuring the frequency from an oscilloscope. So to find the frequency of an alternating power at potential difference, the time-based control must be used. So that means the scale on the x-axis as well as the scale on the y-axis. So the time-based circuit makes the spot move at a steady speed from left to right and then return very quickly from right to left. So that's what produces a sort of your usual wibbly wobbly wave that you're used to seeing. The time-based circuit, which is built into the cathode ray oscilloscope, can be adjusted to give different times for the spot to travel across the screen even. The time-based control indicates the time it takes the spot to travel a distance of 1 division from left to right, i.e. if the control indicates 10 milliseconds per division, this means that the spot will move 1 division from left to right in 10 milliseconds. And across the whole screen, in this case, of 10 divisions in 100 milliseconds. So it means each box is worth 10 milliseconds, just like we did with the voltage. Right, so let's do some examples here. So study the trace shown on the CRO, cathode ray oscilloscope, opposite. Note the number of divisions the spot moves from left to right in one complete cycle of the alternating signal. So that's one wavelength. And for the time-based setting shown, find the time in seconds for one complete cycle, because we know that that is a time period. So it's time for one wave to pass is the time period, thinking back to National 5. Then from that time, if you find the time period, capital T, you find the frequency using capital T period equals 1 over the frequency. Okay, so in the case of the top one, if we look at, we're just concentrating on one wave. There. Okay, so how many boxes does that one wave span? 1, 2, 3, 4 boxes. Okay, and each box is worth 10 milliseconds. So for the time base, we've got 4 boxes. So 4 times 10 milliseconds. So 40 milliseconds in one wave. Okay, so that's time period. So the time period is 40 milliseconds. But remember, for frequency, we need it in seconds. So 40 times 10 to the minus 3. So the frequency, if time period is 1 over frequency, frequency is 1 over time period. So 1 over 40 times 10 to the minus 3, which comes to 25 hertz. And that's how you find the frequency from an oscilloscope. You find the time period by counting up how many boxes one wave spans, and then timesing it by how much each box is worth, and then doing frequencies 1 over time period. So another example here. So we've got a slightly wider wave. So one full wave spans that many boxes. So that's 1, 2, 3, 4, 5, 6, 7, 8 boxes. So one wave is 8 boxes. And each box is 5 milliseconds. So per division. So one wave is 8 times 5 milliseconds. So 40 milliseconds again. So time period is 40 milliseconds, so 40 times 10 to the minus 3 seconds. So the frequency is 1 over the time period, so 1 over 40 times 10 to the minus 3, which again, because maths doesn't change, is 25 hertz. So you guys are going to have a go at some of these questions. They should be nice and straightforward.